It's the most common form of energy around. These thermograms are a special film technique to make heat visible. The colors represent temperature. Red is hot, blue is cold. We generate heat energy to do work, but we also throw tremendous amounts of it away. Every piece of technology that we've looked at so far produces heat, sometimes on purpose, sometimes not. Whenever work is done by a machine, some of the energy to do that work goes into generating heat. The heat may be the result of resistance or the friction of moving parts. In other systems, it could be produced by the electrical resistance in wires. Whenever energy is changed from one form to another, some heat is produced. Sometimes energy seems to disappear, but heat is usually the culprit. Take, for example, the wrecking ball. It's given potential energy. It becomes kinetic energy, which does work breaking the concrete. But suppose the concrete doesn't break. The energy doesn't disappear, it becomes heat. This is why no machine is 100% efficient. The work out is never the same as the work in. Some of that work was lost making heat. Thermal energy is something like kinetic energy in a mechanical system. It's the energy of motion. But instead of the motion of an object as a whole, thermal energy is the movement of the molecules within the substance itself. Just as an object has more kinetic energy the faster it moves, molecules have more thermal energy the faster they vibrate. Thermal energy can move in three ways. The first is when it travels through solid objects. If heat is added to one end of a rod, the molecules at that end begin to vibrate faster. Those molecules transfer some of their energy to the molecules next to them, and so on down the line. This type of thermal movement is called conduction. Conduction, on a microscopic level, is something like this. The only difference is that molecules keep vibrating after they transfer their energy. Some materials are better conductors than others, depending on their molecular structure. Metals are generally good conductors of heat, while wood is a poor conductor. That's why the end of the stick in your hand doesn't get hot when you roast your hot dog. Poor conductors are good insulators, very handy when we want to slow down the rate of heat movement. The second way that heat moves is by convection. Convection is mostly the movement of a hot substance through a cold one, and works best in fluid systems. Hot air rises because it's lighter than cold air. It simply floats to the top. This is a serious form of pollution, waste heat. The heat from this stack, along with others like it, can actually affect the weather. After all, the weather itself runs largely by the convection of warm and cold air masses pushing each other around the Earth. The third way that heat can move is by radiation. Radiation is not what goes up in smoke. Smoke is carried up by convection of the hot air. Radiation is what you feel off to the side. It's the one form of heat transfer that does not need a medium. In other words, you would still feel the radiation from the fire even if there was no air between you and the flames. That's how we get heat from the sun. It's radiated to us through empty space. These three methods of transferring heat energy: conduction, where it passes through an object by vibrating the molecules; convection, where a warm fluid floats up to the top of a colder one; and radiation, where the energy travels directly through space, are how thermal energy is moved from one place to another. Heat energy is often used for its own sake, like cooking, but usually it's converted into something else, like mechanical energy. That's how an internal combustion engine works. The thermal energy from the rapidly burning gases causes them to expand, create pressure. That does work moving the pistons. When the pistons move, they develop kinetic energy, which does work turning a crankshaft. The crankshaft gains rotational kinetic energy. It then does work turning the drivetrain and the wheels. The final mechanical energy available to move the car is less than 20% of the thermal energy we began with, because 80% of that energy was thrown away as waste heat. When thermal energy is given to a substance, as in steel manufacturing, the big question is, how much energy do you have to put in to raise the substance to the desired temperature? That can be a rather important question considering the cost of producing the heat in the first place. How readily a substance accepts heat depends on its molecular structure. Every substance has a different molecular structure, so it'll have a different ability to absorb the heat. So every material is given a value called heat capacity. Heat capacity not only determines how much heat the substance can hold, but also how readily it will give the heat back up again when you want to cool it down. Sometimes heat energy is available for free. The Earth has its own heat if you don't mind digging for it. And in some locations, this energy can be tapped and turned into electricity. But this is an unusual case. Usually we get heat by burning something like coal. This is a coal-fired generating station. Can you see where heat is being lost? In the next summary program, you will meet a technician who has to identify the heat losses and calculate the efficiency of the plant. But see if you can spot some of them first. Remember, you're looking for losses from friction, conduction, convection, and radiation.